Made easier. Here we can look into the exercise 1.2 under the number system. A quick reminder on the real numbers. What are real numbers? We all know that it is a collection of all the rational numbers and the irrational numbers. Shown here is a sample number line. As you can see, you can find zeros, ones, the positive integers, the negative integers as well. So, where does the real number fit in here? The real number, as we know, they could either be rational numbers or irrational numbers. So, any unique point on the number line is a real number. That is why the number line is also called as a real number line. For example, let's see how do we plot some numbers, the rational numbers and irrational numbers on the number line. I've used the color codes so you can very easily identify where the rational number 0 goes into the number line and numbers like -5, 5 by 2 which is nothing but 2.5, 1 by 7 which is identified by the red color is very neatly defined in the number line. You can even identify the irrational numbers also. So this number line perfectly indicates that it can contain the rational numbers and irrational numbers. Let's look into the problems. State whether the following statements are true or false. Justify your answers. Every irrational number is a real number. Yes, we know that the real numbers is a superset of both the rational numbers like 0 or -20,000 as well as the irrational numbers like pi. Since it is a superset, we can say every irrational number is a real number. The answer to this is true. Question 2. Every point on the number line is of the form root of m, where m is a natural number. The answer to this is false. Let's see why is it false. The given statement is m is a natural number. So, the natural numbers are like 1, 2, 3 and so on up to infinity. It starts from 1 till infinity, all the positive integers. So what they are asking us to find is any number like root 1, root 2 or root 3, they can be found on the number line. It is true. But is it the only numbers that can be found on the number line? No. There could be other numbers like 0 and the negative numbers as well. If we find the square root of a natural number, it will always result in a positive number. So what happens to the negative numbers and numbers like 0 on the number line? How do we derive the negative numbers? The negative numbers on the number line can be expressed as the square of imaginary numbers. Now, what are these imaginary numbers? They are part of yet another classification of complex numbers. Actually, the real numbers come under the complex numbers. The complex numbers are represented in the format a plus ib, where a and b are real numbers. So we can very well understand that real numbers form part of the complex number. But the complex numbers are represented in the format a plus ib, where I is an imaginary number and it takes the value of square root of -1. Since there could be other numbers which could not be expressed as root of m when m is definitely a natural number, the answer to this question, every point on the number line is of the form root m, where m is a natural number, the answer is false. Every real number is an irrational number. How do we answer to questions like this? Immediately, the first thing which should come to your mind is the hierarchy map. If you look into this hierarchy map, you can make out very clearly that the real numbers contain both the rational and irrational numbers. So, since the real numbers contain both the rational and the irrational numbers, a number which is identified as a rational number could also be a real number. So, the above statement is false. Are the square roots of all positive integers irrational? If not, give an example of the square root of a number that is a rational number. The answer to this question is false. Why? The square roots of all positive integers need not be irrational. Say for example, if you consider 25, it is a positive integer, the square root of which is plus or minus 5. We know very well that plus or minus 5 is not an irrational number, but it is a rational number instead. Since the square roots of all the perfect squares are rational, the above statement is false. Show how root 5 can be represented on the number line. First, you need to understand the Pythagoras theorem. It states that in any right angle triangle, the square of the hypotenuse is equal to the sum of the squares on the other two sides. As you can see, the triangle under consideration should be a right angle triangle for the Pythagoras theorem to be proved. The lengthier side is called the hypotenuse. The other two sides, as you can see, one is the perpendicular and the other is the base. Therefore, AC is the hypotenuse, AB is the perpendicular and BC is the base. The Pythagoras theorem states that AC squared is equal to BC squared plus AB squared. Show how root 5 can be represented on the number line. How do we find the solution to this kind of problems? We make use of the Pythagoras theorem because it is a theorem which makes use of the squares of the sides and the hypotenuse. So we can very well make use of the theorem to find solutions for these kind of problems. How do we go about? 5 can be represented as the sum of 4 plus 1, where 4 is a perfect square and 1 by itself is a perfect square. So you can make use of this format for any numbers which can be represented as the sum of two perfect squares where one of the numbers is 1 by itself. So, going forward, how do we make use of the Pythagoras theorem for this sum? We consider the hypotenuse AC as root 5. So, AC squared, I've just replaced AC as 5. So, which makes AC squared is nothing but root 5 squared. Root 5 squared, I can replace it by root of 4 plus 1, the whole square, which is nothing but in place of 5, I've just replaced it with 4 plus 1. Cancelling out the square and the square root, it becomes equal to 4 plus 1. Now we know very well 4 can be represented as a perfect square as 2 squared and 1 also as a perfect square as 1 squared. This kind of a representation maps to the Pythagoras theorem where AC is root 5, AB is 1 and BC is equal to 2, which you can make out from the number line also. From the number line, if you look into, AB is 2 and BC is 1. So, how do we find out the value of root 5 on the number line is, you draw AB with the measurement of 2 and BC with a measurement of 1. Draw the hypotenuse. Now we have derived 2 and 1 using root 5 by using the Pythagoras theorem. So, we know that AC is nothing but root 5. Right. So, take a compass, find out the length of AC and just mark the compass onto the number line. The place where it meets the number line, that is D. The measurement of AD will give the value of root 5. This is how we find the measurement of root numbers on a number line, provided the number can be represented as the sum of any two perfect squares with one being one of the perfect square. But how do we find out for the other numbers other than say root 5? Now you can see root 10 can be expressed as 9 plus 1. 17 can be represented as 16 plus 1. So for these measurements we can find out the same procedure to find the measurement on the number line. But for the other numbers, how do? We just make use of the spiral setup which is represented in the coming example. So we can make use of the other format to find out the measurement of square root numbers on the number line. Let's do this classroom activity, constructing the square root spiral. This is a very simple activity where you measure 1 unit onto the number line and 1 unit perpendicular to the point A. You construct a right angle triangle. Find the hypotenuse. The length will be root 2. Drawing this measurement OB onto the number line intersects the number line at the point P. So we get the measurement of root 2 onto the number line as OP. Using the same procedure, now we can make use of root 2 and 1 as indicated by the green legs. Draw a right angle triangle. The hypotenuse definitely will become root 3. Take a compass, measure this root 3 and extrapolate onto the number line where it can meet the number line at the point Q, where OQ can give the measurement of root 3. This is how you derive the measurement of root 3. Same way, you can keep extending by making the hypotenuse as one of the leg and making 1 unit as the other leg, making it into a right angled triangle. Draw the hypotenuse, mark it onto the number line using a compass. That way we can find out the measurement of all the root numbers. This is called the square root spiral.